let's get into it. Today we're going to pull back the curtain on the digital world and look at something that's, well, it's basically the fundamental organizational system for everything: data structures. They are the invisible architects behind pretty much every single piece of software you use.
I mean, really think about it. How does your computer find that one file among thousands instantly? Or how does your social media app sort through millions of posts to show you exactly what you want to see? The answer, it's not magic. It's a really, really clever system of organization. And that is the core problem that data structures were designed to solve.
You know, at its heart, the definition is actually beautifully simple. A data structure is just a specialized container. Kind of like how you have boxes for shoes and file folders for papers, computers have data structures to hold and organize all their information in memory. They are the absolute essential building blocks.
So, to make this a little more tangible, let's think of them as digital filing cabinets. Each one is designed for a very specific kind of data, and that's what makes everything so efficient and orderly. And what's crucial to understand is that not all these filing cabinets are the same. A programmer has a whole toolkit to choose from. For example, you have an array, which is basically a simple numbered list. Then there's a stack, which works on a last-in, first-out basis. Just think of a pile of plates. And then a queue is first-in, first-out, like a line at a store. You pick the right tool for the right job, right? So you'd use a stack for an undo function or a queue for managing your downloads.
So, what jobs do these tools actually do? Well, their uses can pretty much be boiled down to three main categories. And breaking it down like this really helps clarify their purpose. Let's get into it.
Okay, so first, they store information about the real world. Second, programmers use them as these internal, behind-the-scenes tools to make software actually work. And third, in their most advanced form, they can actually model complex real-life systems.
First up, storing data about physical things. We're talking about information that describes actual stuff outside the computer. Just imagine the massive database the DMV uses for all our driver's licenses, or an inventory system that's tracking every single item in a grocery store. Each person, each can of soup is a piece of data stored in a very specific structure.
Now for the second job, and this one is fascinating because it's completely behind the scenes. Some data structures are really just internal tools for the program itself. You, the user, you never even see them. They're like these secret weapons a programmer uses to make the whole thing run efficiently, like using a temporary structure just to manage memory or sort some data on the fly.
And finally, their third job is modeling. Some data structures are designed to directly mimic real-world situations. A queue, for instance, is absolutely perfect for modeling customers waiting in a bank line or a bunch of documents waiting to be printed, because it follows that exact same first-in, first-out rule.
Okay, so now we know what they do, but how are they classified? Well, the most fundamental difference is between linear and nonlinear structures. And this one distinction dictates literally everything about how they store data and how we can get to it.
So here's the core distinction, right? Linear structures are sequential, like a single file line. Each piece of data is connected only to the one before it and the one after it. Simple. Nonlinear structures, though, are hierarchical. Think more like a branching tree, where one element can be connected to many others.
Because linear structures are all in a sequence, you can go through all the data in a single, predictable pass. It's super simple and direct. An array, that basic numbered list we talked about, is the classic example. And because computer memory itself is sequential, arrays can be incredibly fast for reading data, which is exactly why they're used for so many basic tasks.
Nonlinear structures, on the other hand, are all about relationships. A tree, for example, is hierarchical, just like the file system on your computer. One folder can hold many other folders. A graph is even more flexible, modeling all these many-to-many connections, like a social network where any person can be linked to any other. You can't just go through them in a straight line. You have to navigate the connections, which makes them perfect for representing our super interconnected world.
So, after all that, digital filing cabinets, organizational trees, why should you actually care? Because understanding the basics of how data is structured is really understanding the foundation of the digital world we live in every single day.
So let's just recap the big points. Data structures store real-world info. They act as hidden tools for programmers, and they can even model real-life situations. And their fundamental design, whether they're a straight line or a branching network, is what determines the perfect job for each one.
And really, that's the main takeaway. The efficiency of your GPS, finding the fastest route, the way your music app can shuffle songs, the incredible speed of a web search. It all comes down to choosing the right data structure for the job. They are the silent, powerful engines of our entire digital experience.
So it leaves us with a pretty fascinating thought. These aren't just abstract concepts for computer science class, they are the literal building blocks for creating software and solving problems. Knowing how all these pieces fit together, well, it opens up a whole universe of possibilities.